Hello everyone and welcome to my presentation on sorting algorithms. Today we will cover common sorting algorithms or techniques, their differences and use cases. So, sorting is the process of organizing data in ascending or descending order. It's essential for optimizing tasks like searching, data analysis, and so on. Sorting algorithms are broadly categorized into two categories: quadratic algorithms, which are simple but slower, and divide and conquer methods, which handle large data sets more efficiently. Okay. Quadratic sorting algorithms include bubble, selection, and insertion. They are straightforward but inefficient for large datasets. Bubble sort swap adjacent elements until the list is sorted. Let's see how bubble sort works. In this example, the algorithm compares adjacent elements. As you can see, 29 and 10, 10 and 14, and so on. If the first element is greater than the next, they are swapped. This process is repeated, moving larger elements to the right, like bubble rising to the surface. By the end of each pass, the largest unsorted element is placed in its correct position. This continues until the entire array is sorted, as you can see in this example. As you can see, 29, 37, 37 is 8, 37 will be the biggest number. 29 is the second number. The swapping will continue. Here the swap 14 and then 15, 13 till the end, and then 12, and so on. Selection sort picks the smallest element and places it in the sorted section. Here's how selection sort works. First, the algorithm scans the array to find the smallest element. It swaps this element with the first position in the unsorted part of the array. Then it moves to the next unsorted element and repeats the process. Notice how the sorted section grows one element at a time as the smallest value are placed in order. So this is the first, it will give, and then 8 should be here in 1, and then the 10 will be in position 2, and then 12 and 13, 14, 15, and so on. This is regarding the selection sort. So it actually starts with the smallest index in the unsorted array and sorted, and then move to the next one unsorted. So it will decrease the number of swaps, not like bubble sort. And insertion sort insert each element into its correct position, one at a time. Now let's look at insertion sort. The algorithm starts by treating the first element as a sorted section. It then picks the next unsorted element and compares it backward with the sorted portion, inserting it into the correct position, as you can see in the visualization. This process is repeated until all elements are placed into the sorted section, growing it one step at a time. So as you can see, 10 and then 14 here. Search for the lowest number and then bring it in the correct position. As you can see, 5, 10, 8 will be here between 5 and 10, 12 will be between 10 and 13, and so on. It compares and then insert. While simple to understand, these algorithms are best suited for small or nearly sorted datasets due to their own n square time complexity. That's why they are called quadratic algorithms. Now we can dive to the dive and conquer algorithms like merge, sort, and quicksort. These methods split the datasets into smaller parts, sort them, and then combine the results. They are highly efficient for large datasets with an average time complexity of O n log n. For the merge sort uses the divide and conquer approach. Here is how it works. The array is recursively divided into smaller subarrays until each subarray contains a single element. Then these subarrays are merged in sorted order. As the merging continues, the array becomes fully sorted. This approach is highly efficient, especially for large datasets. So, to see the visualization, let me show you. First, as we said before, we will divide the subarray till it becomes only one single element. So, in half, and then we will start with the left one, and then in half, in half, in half. It become 1, 1, 1. Okay. So after that we will merge it into its correct position. 10 will be in the first, and then 29, and then 10 and 29 and 14. 10 will become first, 14, and then 29. In this approach, as we can see, we actually uses another array, a copy array, to put the elements in it. So that's the limitation of merge, that we need actually more space, more memory. We will continue to divide and conquer until we will have the full array sorted. Lastly, we have quicksort. The algorithm begins by selecting a pivot element. Let's suppose here we choose 13. It partitions the array into two parts, one with elements smaller than the pivot, and another with elements greater than the pivot. The pivot is now in its correct position. When we swap it, this process is repeated recursively for the left and right partitions until the array is fully sorted. So, let's suppose we choose 13 as a pivot. We will move it to the end, and then we will compare. 29 is more than 13, and here 12 is less than 13, so we will swap those two elements, and so on, till all the left portion will be less than the pivot, and the right partition or part will be bigger than the pivot. As you can see, we will continue to make our swapping until these elements is less than 13 and these elements is more than 13. When we swap those two elements, the pivot will be in its correct position. So, in summary, choosing the right sorting algorithm depends on the size and state of your dataset. Quadratic algorithms are simple but slow, while divide and conquer methods are better for large scale data. So thank you for your attention, and this is regarding the sorting algorithms.